Hey guys, welcome to today's lecture on recursion. Hope everyone had a nice weekend. And first I want to ask if anyone has any questions about the workshop, higher order functions 2.
Could we go over get dog breeder, please? Question
Sure.
6.
Sure thing.
Yeah.
So for get dog breeder, I want us to there's some defaults here. Define a function get dog breeder that takes a default name and age and then returns a dog breeder function. The dog breeder function should use the default values defined when the dog breeder was called. Okay, cool. So for this function, it looks like it's going to return a function. So that's why it's called a higher order function, because although it doesn't take a function as a parameter, it returns a separate function.
Yeah.
So get dog breeder, and it'll take a name and an age. And here, does anybody want to guess? I mean, I guess there's multiple ways we can do this. So I guess we want to return a object that has a name and a age. It's a little odd. So I guess if there's no rescue shelter is OD 3. I guess this is kind of a little bit confusing because it looks like this doesn't have a name or an age property. I think that's a typo, maybe. That's what I would initially guess, that it's a typo is the reason why it doesn't have name and age, because I feel like it should still have name and age. Default should be .steve and default age should be 0. Okay, so it's a function that takes a parameter and then it can override. So the return dog breeder function uses default values to find when dog breeder was called. Returns dog breeder function. You can copy over the solution code from dog breeder if you like. Okay, so if you don't give any argument, then it'll just return what was initially passed into it. And then if you do pass parameters into it, then it will overwrite what initially was there. So it can just let's just go with the happy path solution first. So the solution where you do pass in parameters. One thing to note, that it looks like it doesn't matter which order you pass it in. So if you pass in, I'm thinking you have to check the types, because otherwise it's not guaranteed that the first argument will be the name and the second argument will be the age. So I'm thinking you have to check types of what gets passed in. But it looks like in the example, at least, I'm gonna just assume that the first argument is name and the second argument is age for this example, because it looks like it's pretty consistent. Whereas the actual returned function, it looks like it can be whatever in terms of the parameters and what order you pass them in. So I think we're off to a good start here with the dog breeder taking a name and age, and then this can return a function that can take you know, I could just call it param1, param2, because it can be either the name or the age. And then so I could say return, so this actual function is going to return an object, and that object's going to have a name property, and that name is either going to be param1, param2, or name, or the default name. So I guess here I could just define what I want my name to be. So I think there's like a lot of conditionals here, meaning the first scenario is param1 or 2 is a string, in which case that will be my name. So I'll just do the most brute force way for now. Like if param1, if type of param1 is a string, then name equals param1. I'm not sure if they're gonna pass a string as a second parameter, but I could handle that case too. So I could do else if type of param2 is a string, then name equals param2. Else if name was passed in, I guess, is it always guaranteed that there's gonna be, so return function that takes a default name and agent should use a default. Yeah, I'm like confused by this thing, but I'm not sure if this can be optional or not. But if it is, then I'm guessing I'll just use Steve. But I'll say, you know, if name, else if name exists, I guess I can't use name at this point. So this will be like outer name or something, just because I can't use, it'll conflict with like I won't be able to check if it exists or not. So I'm not sure if I'm doing extra stuff than I need to be, but this problem is, it's not, I don't think it's super clear. But yeah, else if outer name, then I'll say name equals outer name. And then finally, if none of these apply, then I guess it's defaulted to Steve. So like else name equals Steve. And then I have to do the same thing for age. Unless they actually don't want the key and the keys name and age here, where then I'd be pretty confused. But then I have to change things around. But yeah, this is a weird problem. So let age, and then kind of do the same thing where if type of param2, if type of param1 is a number, then age equals param1. Else if, and I'm kind of just repeating the same logic, but just checking if it's a number, age equals param2. Else if outer age equals outer age. Else age equals 0. I think that's the default that they wanted. And then I just return name and age from this inner function. And this inner function is what's returned by the outer function. What I'd likely do to clean this up is I'd probably put all this logic into a separate function called like get name, and then do all this logic there so that this could be like just like let name equals get name of, and then passing in everything. So it's a little cleaner, but we don't have to, as long as you guys are aware that once you start doing a lot in one function, that it should probably be broken up into multiple functions. That's just the main idea. And yeah, let's try to see if this works. So yeah, the main idea is I would probably move this into separate function. And the second thing is it's important to go in the right order. So like I would want to check this first because this is the case that takes the highest precedence. So you know, if you pass a function, if you pass a name in to this inner function, then that's the highest precedence. But if you don't pass anything, then there's a second highest precedence, which is the outer name. And if that's also not, it doesn't exist, then the last thing that takes precedence is the default. So the order in which you do this is important. And also, you should always use an else in this case because we're not returning, meaning we're not breaking out of the conditional logic. We're not breaking early if we satisfy a conditional, which means like if we did something like this, then it would be bad because it would, if there's multiple true conditionals, then it would just assign name to the last one. So a lot of times, sometimes we forget to use an else, and then we realize that it'll like reassign name 3 times if all of these are true, which technically it can be true in theory, I guess. So there are times where it's important to use an else if you're not returning, because let's say you were returning and you just said like return name, then you don't need an else, because if that condition is true, then you've returned and you've broken out of checking all the other conditionals. Whereas if you don't return, then you should use else, unless you want the subsequent conditionals to override your earlier ones. Yeah, that's pretty much it for this. This is essentially a function that returns a function, and therefore this get dog reader is a higher order function. Any other problems that you guys would like to have reviewed?
Cache savings.
Cache savings? Okay. So this function, caching is used to temporarily store the result of an expensive operation. So if it's needed in the near future, it can be retrieved from the cache. So this is a very common scenario that happens where basically if you visit a website, there's some images and some expensive media that will just get saved on your browser so that next time you visit, it won't have to go over the network and potentially have to pull that data from a separate computer that isn't local to your own computer. So basically it saves you a lot of time because you don't need to go over the wire, or you don't need to do an expensive calculation. If you've already calculated something, you can just save it, the results of it, so you don't have to go through all of the whole procedure. So they want us to write a function cache savings that is callback and returns a new function that takes 1 argument. When the new function is called for the first time, it should call the callback with the argument and save the result of the function call. The new function is called again with the same argument. The function should retrieve the stored value instead of calling the callback again. Okay, so this is like a practical application of higher order functions, and we'll see what it can do. So it looks like we're having a function here that basically pauses for 3 seconds and then returns a sum. Okay, so it adds 10 after 3 seconds. So it's kind of like mimicking something that would take 3 seconds. Like, let's say you had to, you opened a website and there's a bunch of images. Like, each of those images initially live somewhere else. So like if you open up Facebook and you click on someone's profile and you see all their pictures, like the first time you do that, all those pictures are housed by Facebook somewhere in their computers. And so your computer is going over the internet and asking Facebook to give you those photos, those images, so that you can see it on your own machine. But the next time you come, it might be faster because maybe they save those images already on your browser as static assets. So your computer just has to go to your browser to get it instead of going to your over the wire, like however many miles to the closest Facebook asset storing machines. So it's kind of mimicking that, an expensive function. And basically this cache savings function is going to take this function in as a parameter, and then it's going to return a cached version of that function, so that so essentially this function will take the same parameter as the function that gets passed in as a parameter. It takes the same arguments, but the cool thing is that when you do something, when you pass in the same parameter for the second time, it'll save that parameter and it will save the value versus having to recalculate everything again. So let's try this out. It wants to, so it takes a callback, right, as a parameter. And basically when people talk about caching, I mean, it's a very complex subject, but for now we can think of using objects as our cache, because the cool thing about objects is that when let's say, you have an object called your cache, right? Now you can say, oh, like when I pass in 10 as a parameter, my answer was 100, let's say. So I can store those things in key value pairs where it's very easy to access. And accessing a key in an object is instantaneous, meaning the lookup time is instant, regardless of how big the object is, if you know what the key is that you're looking for. So let's say you stored 100 and the value of that is 1,000. Like let's say this is a function that multiplies something by 10. And you store 1,000, and for 1,000 it's 10,000 is the answer. So like now you have a cache, because if you want to get the value of 10 times 1,000, you don't have to actually compute that, because you've already computed it. And when you first computed it, you stored it as the value of this object. So next time you could just, if you just know what you're looking for, 1,000, then you could immediately get 10,000. So like another more practical example could be like, let's say we're filing taxes, and like we have our 2010 tax return and 2011, 2012. So like when you use TurboTax or any type of tax professional to calculate your taxes, there's a lot of inputs, and the calculation process isn't trivial. I mean, I guess depending on how many assets you have and all these things, it could be really complex how much taxes you owe or are owed. So that calculation could be like a really long function. Let's say that TurboTax created some proprietary function that just goes through all of your inputs, takes your income, takes your children, takes your how much debt you paid, and all these different things, how much charity you gave, and it outputs how much taxes you owe. But once you output that, right? Let's say I want to check again what my 2010 tax return is. I don't want to calculate that each time because I've already done it once, and I can store it now as a value of in this object. And now next time I say give me my 2010 taxes, I could just do cash 2010, and that should give me my tax refund without me having to recalculate it again. And I mean, you could store it as an array too. You could say let cash equals an array and then say like 2010. I mean, it'd be, so, it'd be kind of funky, but you could do something like, 2010, 100. I mean, I don't know why you'd want to do this because it just makes it more confusing, but let's say you did, right? Let's say you did do it like this, and you could, in theory, do it like this. But the drawback here is that when you are looking for 2010, it's going to, basically, you have to use like dot index of, or you have to use, you have to basically iterate through each element in the array to see if this element contains the 2010 tax return. So basically, if you had 5,000 years of tax returns, let's say, and you had to go through each element to see, are you the 2010 tax return? Are you the 2010 tax return? That's theoretically going to take a long time if the array is really big. So that's why objects are really useful for caches, because you can instantly access, using a key, you can instantly access this value without having to iterate through each entry, as you would have to do if you were using an array as a cache. Feel free to stop me if this is getting confusing, but for now, I'm just gonna approach this problem now. So we have our callback function, and we know that we're gonna return a function that takes an argument, and then we're basically gonna, initially we're gonna call the callback. Initially we're gonna have to let the result equals callback arg initially, but that's calling our function. This is gonna be expensive, but let's just go with a non-cached version. So we don't even, this is the non-cached version, but it will work. Basically, we're saying, okay, it's just like a bunch of, I mean, this would be kind of useless to ever do, but basically this will get you the right answer. It will just, and let me see if it actually works. I'm not sure how they're gonna actually check that it's not doing it. Oh yeah, they're checking if your function is called. Okay, so they do check. So, but this is the non-cached version where essentially you're passing in a function, and then, which is, cache savings adds 10. So callback would be adds 10. And then when you're returning a function that takes an argument, which is cached adds, and that takes 20, right? And so that's going to call your callback with 20. So it's going to call adds 10 with 20. But the problem here is that there's no caching going on. So here I could say let cache is my object, first of all. And then I could say so the first thing I should do before I even calculate my function or execute my callback is I should check if cache arg, meaning if this argument exists in my cache, then I could just return it. So if 20, which returns 30, exists in my cache, so if I do cache adds 20 and that exists in my cache, then I just return the value of the key 20.
Oh, okay. So 20 is the key.
Yeah, 20 is the key, exactly.
Oh, okay.
So it's instantaneous. I'm not doing any calculation. I'm not calling the function because I've already called it in some previous instance, and now this thing is saved, right? This cache is saved, and so I will essentially be able to access that key and get that value. But let's say it doesn't exist, right? Like, so we never ever calculated 20 before. So it doesn't know what the value of 20 is because it hasn't calculated it. In that case, then we have to set cache arg equals callback. Now we have to actually call it because we don't have that as a property right now, so we're setting it, and then we can just return cache arg. So I guess this could be formatted a little better. So I could say if it doesn't exist, right, then do this. And then, yeah, that's basically it. So if it doesn't exist, set it, call it. If it does exist, then just it'll just go here. It won't go into here if it does exist, and so it'll just return the cache arg. So let's go a little bit deeper into this because I know this can be confusing because let's walk through what happens when we pass in a function in here. So let's say, we say const adds 10 equals adds 10, right? How they're doing it. So let cache adds 10 equals cache savings adds 10. So we pass in our function. Now we say now let's see what happens when we do all these things. Let's walk through it together. So when we call the function now, cached adds with 20, then what's happening? Well, we're actually executing this inner function, right? Because that's the function that we've returned from the cache savings. We're actually executing this inner one because in line 14, now we're invoking it with 20. And so arg is 20. And we're checking, does 20 exist in the cache? It doesn't, because we've never called 20 before. So we've never populated the cache with 20. So it's false. So then it sets it. So now cache becomes 20, whatever the outcome of 20 is, which is 30, I think, because we're setting it here. Because now we're calling the function adds 10, passing in 20, and now cache is 20, 30. And then we're just returning the cache 20, which is 30. So that's the first time, but it's going to call the callback. Now when we do arg equals 10, same thing as before. Like 10 doesn't exist because cache is 20, 30 right now. So it goes in here and it sets 10 to be 20, or 0 is going to be 10.
Yeah, 0 is going to be 10.
Yeah, 0 is going to be 10. And then now when we pass 20 again, cache is going to have 20. So this is going to be false because cache does have 20. So it's just going to return cache 20. And cache 20 looks like this right now when we call it. The reason being, this doesn't get reset each time because you're only calling cache savings once. You're calling cache savings once, and that's initializing cache as an empty object. Now, the rest of the times you're actually invoking this inner function, and so it will always have access to the cache and the populated cache because it's not like you're calling this function again. If you were to call cache savings again, then it would reset your cache, which means like you wouldn't be able to save anything in your cache because your function is being called and this line 4 is being run every time. And so it's reinitializing your cache as an empty object each time, so it wouldn't work. But the reason this works is because you're passing a function, you're returning a function from it and you're calling that function, and this function itself does not reset the cache. It doesn't set the cache to be an empty object. So it will always maintain a reference to the object that was initialized when this function was first called. And if we're updating that object, it won't reinitialize it to an empty object. So it'll always have that like saved version of the object's state after, you know, this function was invoked multiple times and this cache was mutated multiple times. Always it'll have reference to that cache that has all the keys populated, because again, we're only calling this cache savings function once and initializing the cache only once. But yeah, this kind of thing is cool because it actually helps your performance of your application. It makes it faster, and it'll be noticeable. Granted, like a lot of stuff already optimizes for performance kind of out of the box, but it can bring benefits, noticeable benefits to the performance of your application. However, it will add complexity to your application. So there's always a trade-off. If you want to use some fast, fancy cache and trying to over-optimize things, then your code's gonna start looking real confusing, because this is a simple cache, but there's other more. It could get more confusing, and then you can muddle your logic. But if you use the proper abstractions and hide away the complexity in functions and things like that, it's maintainable. But yeah, I think this kind of stuff's pretty cool. Is there any other questions that you guys want to go over from the problems? If not, then we'll start on recursion, which is one of my favorite topics, but also one of the most frustrating topics when I was first learning it. But I think it teaches a new way to think about things and sort of opens up a whole different avenue of problem solving. So let's get started. So recursion is basically it's basically solving a problem using a function, and within that function calling the same function.
Mm-hmm.
So yeah, it occurs when a function calls itself, and it's an alternative to using an iteration. So you can, for the most part, and I don't want to say always, because there's usually some type of exception to rules, but usually you can solve anything with recursion that you can solve with a loop as well, and vice versa. Like if you can solve something with a loop, you could also use recursion. If you could solve something with recursion, you could also solve it with a loop. Now there can be functions where it uses a loop but is also recursive. Those start getting like real confusing. But for now, we'll just keep it as defining it as a tool in the toolbox. Some problems are a little more suitable to use recursion, and some are not. But basically, it's helpful to know this because it helps you think in terms of like breaking down a big problem into smaller chunks. sometimes it's easier to read than an iterative solution because um, some iterations can get hairy. You know, if you're doing multiple nested for loops, or if you have all these like I, j variables floating around, it's a little heavy sometimes on the cognitive load. So using recursion, using the function itself, can actually read easier. But yeah, it has trade-offs. It's fancy because sometimes, you know, it's so elegant in terms of you using the function that you defined within itself. It's, you know, it can get fancy, but at the same time it can hurt you because it can negatively affect performance. So it can in theory take up a lot of memory, and we'll see why that is. Yeah, it has a lot of real world applications, and there's a popular branch of problem solving and interview questions that require you to traverse tree like structures, and recursion is a favored approach to basically traverse these tree like structures, and a lot of structures in general you could traverse using recursion. So yeah. So before we talk about the recursion, we have to understand what exactly is happening under the hood a little bit. So we have to peel back some layers of abstractions and figure out how the language deals with functions. And basically, JavaScript is single threaded, meaning only one function ever runs at one time. So the language focuses on a single function at any given point, only one of them, meaning it only executes one function at a single given point. And the call stack is a data structure that JavaScript uses to figure out which function should be running at a particular point in time. So you can imagine like a stack of pancakes. You could imagine a stack of books, a stack of anything. So basically, you know, let's say you have a stack of pancakes, like 5 pancakes, and then someone else stacks another one, the 6th one, then it goes to the top. So that's the same thing with functions. Basically, when we call a function, it's added to the top of the call stack. And JavaScript will execute whatever is on the top. And we're going to go into more examples. I know it's hard to picture this right now, but basically, well, let me move my thing so these examples will be visible. So we can imagine the call stack like this. And basically when we call, what the heck? Basically when we call first, because first is the first one that's called, right? Second is second. So because JavaScript executes top down, and so, you know, we define our functions and from lines 7 through 12. And then on line 13, when we call first, that puts first on the call stack. So it's like your first pancake, it's your first book, it's your first, you know, whatever you stack on top of each other, your first block, first brick. And it will log I am first into the console. And once it does that, it's done. So when a function is done running, it gets popped from the call stack. Only when it's done, though. It can't get popped if it's not done. So as we can see in line 7 through 9, all it does is log, and then it's done. It's done running. There's nothing else left to execute. So we pop it off the call stack, and then we put second on the call stack. And then the same thing happens. It logs I am second, and then it gets popped off. So this is the preliminary simple scenario here. Now let's get a little more involved. So here we have first, it gets placed on the call stack when we call it. But now what do we think happens when we go to, what's the first thing that happens when we call first?
Log IM first.
Yep, we log IM first. And now what's the second thing that happens?
It gets popped off.
Close.
Oh, first is finished. No.
No, line 3, right? So we did line 2, IM first, and then we do line 3. So what happens when we hit line 3?
Oh, I am second.
Right. But what happens in terms of the call stack?
Oh, it adds it to the top, right?
Yep, it adds it to the top, and we can't pop first because we're not done with first. So we have to keep it on. So like basically JavaScript is, it doesn't have, it doesn't finish something thoroughly. It like will finish it halfway, and then if something else gets called, it has to deal with that next one. And if you think about it, you have to do it like that, because otherwise, in this case, if you have to run second to be done with first, so we can't pop first off because it will never be done until second is done. So it's kind of like a dependency. So we're done logging, but now we have to put second on the call stack. And then what do you think happens next?
Console logs I am second.
Yep, perfect. So yeah, it console logs I'm second. And then now what would happen in terms of the call stack? Because we're pretty much done with like executing second.
Oh, so then it would first is finished though, right?
Almost. But what happens before that in terms of the call stack? What happens when a function is done running?
It popped off.
Yeah, it gets popped off. So basically, first was like paused, if that makes sense, while second was done running, because we had to refocus our attention on second now, because that is what came up to us and said, hey, like execute me, because I'm part of first and you're executing first, so you have to execute me. There's actually no choice. JavaScript just has to execute it. So it gets popped off, and then now what happens? Any takers? So second's done running.
Is it gonna run first? Pops it back on into the call stack?
First never actually left the call stack. It always was there because it never finished yet. So it was always there. But so yeah, like it is on the call stack right now. And basically we're done with second. So what happens next?
So then we
Now it
console
goes
log
back to first.
What was that? Sorry, I couldn't catch that.
I said it goes back to first.
Yeah, it goes back. Like the focus of the JavaScript executor goes back to first, and then what line would run?
Then it'll say I'm first.
It would go close. It would log first is finished because
line 4.
Yeah, line 4, because it's not gonna run it from the top again, because it was already it like knew where it was when it left off. So like it keeps a bookmark, like I'm here in the first function, but now I need to go switch gears to the second function. But when I come back, I'm gonna come back to where I already was. He first already logged I am first, and then it pushed second onto the call stack, and then second ran I am second, and then it popped second off, and now it's gonna finish it off and run first is finished.
Oh.
And then it's gonna get popped off, and then we're done. And like this idea is the same in recursion, but it just happens that second would be first. It would be itself. But in terms of what happens in the call stack, it's the exact same thing. It's only confusing because it is the function itself, which is by its very nature like unintuitive and confusing. But if we can get past that, it's not any different from a function calling a different function in terms of like how it looks in the call stack. It's actually the very same thing in terms of what the call stack looks like. And we'll see the importance of this and why it's a memory hog. That actually has a lot to do with the call stack. But yeah, we can initially, it's hard to think of recursion, but we can just think of it as essentially identical to a function calling a different function. And that concept, I feel like, is a little less foreign. So we could just pretend that like it's calling a different function when in reality it will be calling itself. But in terms of how the call stack looks, it'll behave the exact same way. So this is just a function that will count from 5 to 1, and it does this iteratively. But we know how to do this already, and this is a lot of it's not necessarily the shortest code to write because you have to initialize all these variables and things like that. So how could we write this without using a for loop, but just calling the function itself? We'll learn how to do that. So now, as we can see here, this is recursion basically. We're almost at recursion, but this is what recursion is gonna do. It's gonna call the same function, but it's just gonna pass in a different parameter. And because the parameter is different, it's gonna do something different. It's gonna output something different. But the core essence of this function doesn't change with the different parameters. And so we can just use the function itself to solve it. And so in this way, we manually do this, right? So that's not the greatest solution, because what if we wanted to count down from 5,000? Then are we gonna sit there and type all these out ourselves?
Mhm.
We probably don't want to do that. So now let's try to extend this brute force solution out. But even though lines 8 through 12, we're calling it manually, the JavaScript executor is going to do the same thing, but it'll handle doing that. But it's basically doing the same thing. It's just you're just using the same function, but passing in different arguments. So how do we change the arguments in between calls? Well, we have to subtract, right? We have to subtract by 1 each time. So basically this will log console log 5, right? And then it'll call countdown 4. And so that will call countdown. So let's see what happens in the call stack. Basically, we call countdown 5, that logs 5. And then we call countdown 4. Notice that we can't pop countdown 5 off because countdown 5 calls countdown 4. And in order to pop countdown 5, we need to be done with countdown 4. So we aren't done with countdown 4 yet, so we can't pop. It's like basically countdown 5 gets called on line 10. It gets stuck there until countdown 4 returns. But the trick here is that countdown 4 also can't return until countdown 3 returns. So it's gonna continuously pile things onto the call stack, and it will never start popping off until a function is done, and it's not done because the function that it's calling isn't done, which is why there's a huge problem with this implementation, because it's just gonna go on forever. There's no stop case. So an important thing about recursion, number one, it's not that different from calling a separate function. In terms of what happens in the call stack, it's actually the very same thing. And number two is that you always need a condition where you do not call the function. because otherwise you're going to keep calling the function and you're never going to stop. So you need like, it's called a base case, and you guys may have heard of it, but you need a case where you don't call the function again. And so that's the problem with this one, is it's kind of working, right? Because it's logging everything, but it's just going to keep putting more and more things on the call stack, and it can never pop from the call stack because the function is never done. Because for it to be done, 4 has to be done. But unfortunately, when we call for 4 to be done, 3 has to be done. But unfortunately and it goes on and on forever, because the function can't be popped off until every single function within it has finished executing. And like in this case, that will never be the case. So yeah, and then it just breaks, because eventually, like it'll break at much lower number than this, but eventually you run out of memory, and then your computer will just, your program will just crash. So we're almost there, but this is the perfect solution, where basically you have a base case where, when the number is less than 1, it will just console log done, and that's it. It's not going to call the function again, which means it's done. And so it can start getting popped off the call stack. So let's go through an example here. So when we call countdown 3, it gets put on the call stack. And then we run line 9 because 3 is not less than 1. So we log 3 to the console, and then we call countdown 2. So what do you think happens when we call countdown 2?
It checks to see if it's less than 1.
Yep, but in terms of the call stack.
Oh, it goes on top.
Yep, it goes on top. And then we do the same check like you said. It fails the check because 2 is greater than 1. So it logs 2, and then it calls countdown 1, and it places countdown 1 on the top of the call stack. And then it logs 1, and then it calls countdown 0. Now, what do you think happens when we call countdown 0?
So
done, yeah.
Done.
We're done. And so what happens when a function is done running? In terms of the call stack.
Pops off.
Mm-hmm. So 0 can get popped. And the cool thing is, countdown 1 was frozen, right? It was paused while 0 was running. So if you can think about like line 10, for when the function was countdown of 1, so when the parameter was 1, 10 was countdown 0, right? But the cool thing is countdown 0 just finished running. So now we're done with countdown 1 because countdown 0 is done. So if countdown 0 is done, so is countdown 1, because 10 is the last line. And once the function on 10 is ran to completion, then we're done with that function, that particular invocation where the parameter is 1. And so that's done. So we pop 1 off. And the cool thing is line 10, when the parameter is 2, is countdown of 1. But we just popped 1 off, like we finished 1. So it's like a chain reaction. Like once the base case is hit and that function completes, then everything else can complete too, because 0 depended on 1 and 1 depended on 2, or like actually it's 1 depended on 0 and 2 depended on 1 and 3 depended on 2. So like once one thing gets returned, then its parent, we can call it a parent, whoever called it, can also return, and so on all the way down the chain. And we're done. So yes, this is a little blurb. You always need to find a base case, meaning there needs to be a case where you do not call the function. but you just return some value, like return 0, or return an empty array, or return an empty string, or return 1, or return nothing, just return. You need to end the function somehow. You can't always call the function again, because then it's just never going to end. And when you do call a recursive case, you need to change the input so that it gets closer to the base case, because otherwise you will never hit the base case. So you need to somehow work proactively in a way such that each recursive call brings you closer to the base case. And now let's look at returning from recursive calls. So for this, I think there's a cool example that we could think about when we actually need to return, because before we were just console logging, and so it was a little more simple. But for returning, we could think of it something like this. So let's say you're in a movie theater and you want to know which row you're sitting in, right? But like, you could leave the row and then start counting like down the rows. Let's say, or you could, if you could see all the rows too, you could just iterate. It's kind of like the iterative way where you just kind of count down how many rows you are. But a recursive method could be to ask the person in front of you what row they're in. And what row you're in is just 1 plus whatever they say.
Yeah.
But that person that you asked also doesn't know. So he asks the person in front of him, and so on. And the base case is the person in the first row, because he has no one to ask. So he says he knows what row he's in. It's the first row. So basically, let's say you're in like row, you're all like, let's say, I don't know how to, maybe we'll just say these are all the rows. And you're here. And so you ask this person what row they're in, and this person doesn't know. So he asks this person what row they're in, and this person asks this person, and this person asks this person. It's the same recursive function, which is the asking part. And this person now returns back 1. Returns back 1. And so now this guy is like, okay, I got 1, so I'm gonna return back 2 because I'm 2, based on just the fact that you're 1 plus whatever the row is in front of you. And then this guy will now return back 3, and this guy will now return back 4. And then this guy will now return back 5, and now you're 6 because you just add 1 to whatever the person in front of you has said. So it kind of like, that's kind of like how recursion works, is like you call all these functions and they like stack on top of each other because they haven't completed running yet. And then once that last function returns a value back to the second to last function, then that function can be popped off. And now you could think of this as like popping off the stack. And like now when they start returning, it's like popping off the stack. And then when they actually aren't returning, it's like pushing onto the stack. Like, hey, I'm asking you. Okay, hey, I'm asking you. Okay, hey, I'm asking you. Hey, I'm asking you. And we're pushing onto the stack. But once that last person is found and that person's like, okay, like if the buck stops here, I'm 1. Because that's just a rule. Like there's nothing in front of me, so I need to establish this rule that like if there's nothing in front of me, return 1. And so I'm gonna return 1, and I've returned, so I've completed running. I'm not calling any other function. I'm not putting anything else on the call stack. So now I'm popping off. Like I return to the caller, and then I pop. I'm done. Like I'm no longer useful. I've done my job. And then this person can now return. Can you guys still hear me?
Yes.
Okay. This person returns, and now I've that guy is no longer relevant because he's done his job. He's given me his row, and he can get popped off the stack. And so it's going to work much in the same way. So yeah, again, base case. The base case in the movie example was the guy in the first row. There's no row in front of him, therefore his value is 1. He doesn't he's not going to ask someone. So let's try and solve a problem, a different problem using this concept. So we're going to this is a classic example of recursion is factorial, where we have factorial of a number is that number times the factorial of the previous number.
Yeah.
So yeah, that's kind of like the rule of factorials is it's 5 times, for 5 it's 5 times 4 times 3 times 2 times 1. For 4 it's 4 times 3 times 2 times 1. But if we kind of group these together, we can see that 4 is actually 4 times 3 factorial, because 3 factorial is 3 times 2 times 1. So if we just substitute that into 3 times 2 times 1 of 4 factorial, then we get that 4 times 3 factorial is how we calculate that. So what are our base cases in this case?
So it would be if num is equal to 0, return 1, right?
Yeah, exactly. And also 1 is also just the base case. Yes, it's just going to return 1. So we could just say, if num equals 0 or if num equals 1, then return 1.
Mm-hmm.
So that's simple enough. And we always want to start simple. So, this is 1, 1, does nothing else. But now we need our recursive case, and we know that based on this pattern that factorial is that number that was passed in as a parameter times the factorial of that number minus 1. So here in this recursive case, we need to get closer. So let's just pretend that the next simplest case, which is factorial of 2, was passed in. Then what would we put here? Are there any guesses? So if we have 0 or 1, then we're going to return 1. But let's say we pass 2 in. Then what should we do in line 6?
Return 2.
That will give you the right answer in this case, because I believe factorial 2 is 2, but it needs to be extendable. So that's close, but if we pass 3, then it wouldn't work, right? Because it would just be, you would just return 2 still. So the answer is right, but how would we make it extensible so that it would work for other parameters as well?
We do num time parentheses num minus 1.
Yeah, that's very close. You're getting very close now. So then that would be factorial 5 would be 5 times 4, but it needs to be 5 times 4 times 3 times 2 times 1.
Okay, we need to call the factorial, and then pass it an argument of I think num minus 1.
Yeah, perfect. So basically we could just do num times factorial of num minus 1. So yeah, this is just showing that it will be undefined because we don't have a case for that. So we don't return anything. So when we don't return anything, it's just undefined. But here we see that if we just call factorial of num minus 1, then it will be close, but it won't be quite right, because factorial is actually the num times factorial of num minus 1. So it's close, but also the reason why this is wrong is because you can't console log it. You actually need to return it, because basically the countdown example was a little confusing because they only wanted you to log it. Like, they didn't care about returning anything. But in this function, you actually need to return like an output. So you can't just log it, because then when you try to set it to something, like, it'll be undefined because you're not returning. So again, this is closer, but you basically just.
So we do else return num times factorial parentheses num minus 1.
Yeah, exactly. I mean, this is just the same thing that you just said, except they're just setting it to a result variable, which I think is not that terribly useful in this case, but I guess it is descriptive. But you could just return num times factorial num minus 1. And you need to return, again, because it's the same concept of the movie theater example, right? Because basically you want to get back your row, right? You need to get that returned back to you. You can't just I guess in theory, right? Like the console log example is like them shouting it out. Like, I'm row 0, I'm row 1, I'm row 2. But let's say you were deaf. Then somebody needs to give you like a block that has the number on it so you can like feel it out. Because let's say you're deaf. Then you need to get back something tangible. You can't just have it logged out and you can't do anything with that, because in this case, like, you can't hear. So the console log example is like, it could still work given that you'll still see it in your logs, like in your output of your terminal, you'll still see the correct value, right? Whatever row you're in, because they're shouting it out. They're not giving you back anything tangible, but they're shouting it out. But in programming, you often need to call a function and then get the result of that function, store it in a variable somewhere, and then use it next time. You can't just hang on to it like it's in air. It's in the air, but you can't do anything with it. So you need like something tangible that gets returned back to you. So therefore, this is the return. This is the purpose of the return, is that it's giving you back something that you can then store in a variable somewhere or save in a cache maybe somewhere, right? Like, you need to get something back from the function to actually store it. Whereas if you just logged it, then you know what the value is if you were checking your console at that moment, but you can't do anything with it. So yeah, you could have console logged and it would print you this thing, but in this case, we can't even do that, because the function is actually used as a value. Because if you look at line 8, factorial num minus 1, that invocation needs to be interchangeable with an actual value, or else you'd be doing num times undefined. So you need, when you're actually doing calculations with a recursive call, so beforehand in the countdown function, we weren't doing any calculations with the recursive call. We were just calling it, and that's it. But in this case, we're actually multiplying it by a number. So we need it to return something, or else factorial of num minus 1 will always be undefined, and we can't multiply undefined to a number. So if we're doing anything in terms of like pushing something, or a arithmetic operation, or if we're like aggregating the results of something, like, right, then we need to return something, or otherwise what's that function invocation's value? Like, it needs to have an actual value, which is why we need a return in this case. So yeah, this will log 2. And now let's take a closer look at what's happening with something a little more larger and what the call stack will look like. So when we call factorial of 5, that's going to run line 7, right? Because line 3 is not true. So it's going to go to line 7 and it's going to say result equals 5 times factorial 4. And right there, it's going to freeze the invocation of the execution of factorial 5. Because now we've called factorial 4. And we're not done with factorial 5 yet. So factorial 5 stays on the call stack. And then we run factorial 4. So does anyone want to take a stab at what happens in the call stack after factorial 5 is called? And after line 7 runs, what happens with the call stack?
It will like store like into memory.
Yep, exactly. And then what will happen next? What's the next step after factorial 5?
It will go to 4.
Yep, exactly. So now we push factorial 4 on the call stack. But we aren't done yet because factorial 4 itself calls factorial 3, right? Because when we run factorial 4, it does 4 times factorial 3, but then that's when it freezes. It pauses factorial 4 at that exact moment, line 7, and it says, okay, now I need to shift gears to factorial 3. Because, JavaScript, again, it only executes what's on the top of the call stack, and it does not pop until it's done running every single function in that execution context. So we're not done with factorial 4, but we switch gears to factorial 3. So what happens next in terms of the call stack for factorial 3 when it gets called?
It will detect, and then call factorial 2.
Yep, exactly. It does the same thing. Puts factorial 3 on the call stack, calls factorial 2. Same thing happens here. Now, what's the interesting part about this case? What happens when we call factorial 1?
Fine. Right?
What was that?
When we call factorial 1, that's the base case. So then it's stop, and then it will return like the results from the top to the bottom.
Exactly. It returns the result from the top to the bottom. So factorial 1, if you look up at the bottom, at the top right, it says factorial 1. That becomes 1. Like it becomes interchangeable with 1 because it returns 1, right? So 1 and factorial 1 are the same thing, basically. 1 and the invocation of factorial 1 is the same thing. So now factorial 2, what's the value of factorial 2?
Is 2.
Yeah. So now factorial 2 has a value. So now you can see the domino effect. Like everything can start getting popped off because factorial 2 depends on factorial 1 to complete. But factorial 1 has completed, right? It's 1. It doesn't call anything else. So factorial 1 becomes 1, and now factorial 2 can complete because factorial 2 is now just a number. It's 2, and it gets returned to factorial 3. Like it gets returned in the context of factorial 3. So factorial 2 becomes 2, and then so factorial 2 becomes 2, and 2 gets substituted in for factorial 2 because they're the same things now because they finally returned, thus enabling the function to become its return value. And once that happens, the function is done running. And once the function is done running, it can pop off the call stack. So in this case, factorial 2 became 2. And now factorial 3 is done running because factorial 3 was stuck on line 7, right? because factorial 3 was like waiting for factorial 2 to get done. And factorial 2 was waiting on factorial 1 to get done. But once factorial 1 got done, then it said, okay, now factorial 2 you can complete. And then factorial 2 was like, okay, now factorial 3 you can complete. So now factorial 3 is 6 and it's completed. It gets wiped off. We don't need it anymore. And the same thing with factorial 4, and then the same thing with factorial 5, and then we actually are done. And we get 120. So it's kind of like the movie theater example. Like you start building it up as you're asking, and then the person in front of you asks the person in front of them, the person in front of them asks the person in front of them. And these people, they are on edge. Like they're not completely relaxed until they get their number back. So they're just hanging around. They're like they're waiting. They're not done. They're paused. They're paused while the other people keep asking down the line until that final person says like, okay, I'm row 1. He turns around to row 2. He's like, I'm row 1, and row 2 is like, thank you. Like I'm done now. I can finally like watch the movie. Like I'm done executing. And so he turns around to row 3 and says like, look, I'm row 2. I'm gonna watch the movie now. Like I don't care. You guys handle your own thing. And then he turns around and watches the movie, which is kind of synonymous for like getting popped off the call stack, and like we don't have to care about him anymore. And then it's just like a domino effect. It goes up, it builds it up, and then once that return value is hit, it starts breaking it down. Now we can see that it's expensive, right? Because you have to hold all those things in the call stack, meaning like that every single entry in the call stack takes memory. And like if you can't pop a function off a call stack until all these other functions get popped off, then like you could in theory have like a huge memory footprint. But I mean, there's ways around it, using a cache, for example. We kind of did that cache example earlier, but theoretically, if we've already calculated factorial of 4, we could just like look it up in the cache instead of actually calling factorial 4 if we knew its value already and store it in a cache. So yeah, some takeaways. Write your base case first and test it using the simplest cases. So for example, factorial, try to solve factorial 0. Just write your trivial base case out. Then try to solve for factorial 1. Then try to solve for factorial 2. Like go small to big. Don't try to solve it all at once from the most challenging input. Also, always write your base case and always have a case where you don't call a function, because otherwise you're gonna run into a memory overflow. And then yeah, you incrementally test it against more harder inputs. So these are some really useful tips here. So whenever, let's say someone was like, oh, whatever problem you have to solve has to do with arrays or strings. Usually the base case is always an empty array or a string of length 0. So like an empty string. That's a lot of time. I mean, I'm never going to say always, because again, there's always going to be some crazy exception. But for the most part, arrays and strings, the base case is when the array is empty and when the string is empty. So let's say we had to sum the numbers in an array, right? Always start with the easiest possible case. Like that is always going to be helpful. Like don't try to solve the sum of 1, 2, 3, an array of 1, 2, 3. Just try to solve the sum of array of just one thing, right? And then you'll realize that will be the logic that will help you solve an array of 2 things or array of 3 things. So yeah, again, another important thing to remember is when you do call the function again, make sure you're getting closer to the base case, meaning like make sure the parameter you're passing to that function is incrementally getting you to the case where the function will not call itself again. And we saw this example with the not Fibonacci, with damn, why am I blanking on the problem that we just did? Basically,
Factorial?
yeah, factorial. I was like blanking on that word, but every single invocation you did n-1, so that is getting you closer to, with each, factorial 4 will call factorial 3, factorial 3 will call factorial 2, so you're getting closer to that base case. You always need that, otherwise you're just gonna never break the loop or break the recursion. And yeah, nested arrays we can also solve recursively. See the next unit, I believe, will these are some things that we should always take it to heart when we're solving recursion. And this third point is really important too. Whatever type of thing your function returns, your recursive case should return the same type. Meaning, if your base case returns 0, then your recursive case should return a number. If your base case is a string, then your recursive case should return a string type. They should match types, because otherwise, let's say you were doing that multiplication, right? If your base case and your recursive case are different types, then you'd be trying to multiply a number with a string or something. Like, the two things should match up so that if you wanted to do operations like concatenation or arithmetic, you could do it because they're the same data type. Like, you could merge them together, or you could parse them in some way without there being an inconsistency. And yeah, you can use loggers to debug. And if you get stuck, try doing it iteratively. But sometimes if you get stuck, you just have to think like, damn, like this is just the learning process. Like it's not an easy concept, and I'm just gonna have to like struggle right now and like accept the struggle, because eventually like it will start making sense. But there's no magic bullet to say like you're just gonna understand all these recursive problems, because there's gonna be types of problems you're gonna stare at and you're gonna be like, I'm not used to thinking like this. Like I don't know, like I don't even know where to start. That is just part of the struggle, and that is just part of what comes with trying to learn new things. Is like initially it's gonna be really hard. And some of you might come naturally to you guys. I was not one of those people. It was really challenging, but it will definitely start becoming, bit by bit. And it's not even like it'll happen all at once. Like there will be a time where you think you understand it, and then later on you're like, damn, I really didn't understand it. And then there's a lot of different layers to it. The complexity can get really can become really complex, but at the same time, it is a different way of thinking about problems, basically breaking a problem into smaller problems, sub-problems, and then sort of like building that up from like the smallest, most trivial case. And so it's like a different approach, a different way of thinking about things that isn't intuitive, but different. And so I just want to leave with one more example of that array type. So like summing an array, right? So let's just use these steps that we've learned and actually try and apply it. So again, we want to sum all the numbers in an array using a recursive approach. So first thing is, we always want to start simple, right? That was one of the things that it told us to do, is like start with the most trivial case. So if they want you to reverse a string that's empty, or reverse a string that is just length of 1. So in this particular case, nums to sum is just a length of 1. So how do we solve this if our array was just a length of 1? Like, what would we return?
Return array.
Close, but we want to return
0.
Yeah, exactly. Array of 0 is the most trivial case, and that is, we could consider it. So how do we convert this into like more of that base case approach? Like, what conditional could we check here?
Array, if array dot length equal 1,
then yeah, we can return array at 0.
Yes.
Okay, so that's our first step right here. Is we've hit our base case and we tried breaking it down into a very simple component, the most trivial argument, and yeah, now we need to go to the hard part, which is the recursive part. But we need to keep in mind these things. Like, we know it's recursion, so we know we're gonna have to call this function again somehow. That's number 1. Number 2, we know we're gonna have to return, because otherwise the function that's calling it won't be able to interchange that invocation of the child function with a value. So you know you're gonna have to return, because otherwise when you call that child function, and let's say you're gonna like add, right? There'll be nothing to add because you haven't returned anything, because it'd be undefined. So you'd be trying to add something to undefined. So you know you're going to return, you know you're going to call the function again, and you know that you're going to have to break down the parameter so that it gets closer to the base case. Like, that's an important thing to remember. Always try and break down the problem into something that's smaller than the something that's smaller than it was, so that it gets closer to the base case. So now let's make it a little more challenging, where now it's array of length 2, right? So then in this case, we need a return, and we need to call this function again somehow, but we need to pass it a broken down version of array. Like, we need to break it down so it's smaller, right? So
r dot length minus 1.
yeah, we need to pass in an array, so I'm thinking slice. Just slice the first one off, right? So then it becomes like 2. So this becomes 2. We're close, but what will this return? If I pass in an array of 1 and 2, and then I just call recursive sum of array.slice 1, does anyone want to guess what this will return?
Return 2?
Yeah, it'll return 2, and we actually want 3. So you could do something like array 0 plus, and now it'll work for any input, I believe. Because essentially you're saying, like, you have an array of length 1, an array of 1 and 2, and then basically this is equal to the array at 0. The sum of that is equal to the array at 0 plus function of 2. Like, the if you invoke this and you try to sum 1 and 2, that can be broken down into, like, take 1 off and add that to a broken down version of that array. So like function 2, and function 2 is just going to return 2. So this is going to be 1 plus 2. It's going to result in 1 plus 2. If this was 3, then it would be 0 is 1 plus 2, 3. And function of 2, 3 is going to be function of it's going to be 2 plus function of 3, and function of 3 is just going to be 3. Again, it's not like expected to, but I think with enough practice, like it just kind of, with arrays you start thinking, okay, like what if I just like bit off a small piece of the front and then just reran the function against the remaining stuff like that. Those kinds of patterns will just eventually come, but it's not natural. But I think there's probably other ways to do it too, but it just kind of comes with practice too, of just like, yeah, like when you're dealing with arrays, you kind of, you know, want to work incrementally and break things down by 1 each time. But when you do break the thing down by 1, you also need to add something too, because otherwise it wouldn't work. So yeah.
Okay, can I ask a question?
Yeah.
Like, how about if we say like return recursive sum array that length minus 1 instead of slice?
But then you're not passing an array, so you wouldn't be able to sum the elements in an array if you're just passing the length of the array.
Okay, no, I'm talking about R, and then like have like brackets, lengths, R that length minus 1.
Like this?
Yes.
But then it wouldn't be an array. It would be an element of that array. So like this would be it would be a number now at this point.
So okay.
And you can't check the length of a number. Like this thing has to be an array. Do you know what I mean? Like right now you're pulling. So first we're calling recursive sum of 1, 2, 3, for example. That's your first case. But then now your recursive case is calling recursive sum on 3. So that doesn't, the data, the parameters need to be the same type each time.
Okay, so can you explain like how the slice will work?
Yeah. So
Right.
you just do recursive sum array dot slice 1, right? And so
Yes.
let's walk through it. So let's just do recursive sum of 1, 2, 3. So once that gets called, we run line 5. So it basically calls 1, because that's array at 0, plus recursive sum of 2, 3. And recursive sum of 2, 3 is 2 plus recursive sum of 3. And this is 3. Recursive sum, the sum of recursive sum 3 is 3 because that's our base case. It just returns this. It doesn't call it anymore. And so now 3, this thing becomes 3. And recursive sum of 2, 3, 2 plus 3 is 5. So this becomes interchanged with 5. And now we just do 1 plus 5. And that becomes 6. Basically, slice 1 is changing this array to become 2, 3, and the next time it's called, it's going to become 3, because each time you're passing in, each time array is different. First it's 1, 2, 3. So when you slice 1, that means you're taking off everything to the right, I think, and then now you have a smaller array. And then that gets passed in, and slicing 2, 3 becomes 3, and then, yeah.
I thought slice will start like with the like if you put slice 1, it will start the index from 1, and then it will copy of the remaining elements that are on the right side.
Yeah, that's exactly what it does. So if you have 1, 2, 3, and you just slice 1, then it 0. This is 0, so it starts here, 1, and then it copies everything to the right. And so now you have 2, 3. And if you slice 2, 3, 1, then it starts. This is 0, so it won't take 2. And we don't want to, because we want to break down the array into smaller and smaller parts so that we eventually want to get it to like length equals 1. So now this will become 3. And then we don't have to slice anymore because this just returns 3. It's confusing, but again, just gonna have to remember these things of starting with the base case, the simplest case. For the recursive case, making sure that your parameter is getting smaller such that it will eventually hit this base case. And the fact that I'm adding array 0 is just something that you're gonna have to like experiment with. I mean, it's not, there's no method to say like this is how you're gonna get the answer, but you're just gonna have to look at it, stare at it, and be like, okay, so it won't work when I do this, right? So I need to do something else. What could I do? Like, you're gonna have to just experiment at that point, because there's no silver bullet for stuff like that. But there are those small principles that you need to abide by, and then
Let me ask you, why can't we use splice instead of slice?
it doesn't matter. Like, you could use splice, you could use whatever thing you want. I think splice though mutates it, so that might affect things. But yeah, the point wasn't to use slice. Like, it was just like, you need to break down this array into smaller arrays. You could use slice, you can use I use slice because I want to make a copy. Like, I don't want to mutate the array, because if I do, then because all the other functions, their array is now mutated too, like in all the different layers. So I don't want to, like, I just always try and use slice because it copies and it doesn't mutate. But you could use splice and see if it works. I'm not sure off the top of my head how that would affect the subsequent calls. But yeah, you could whatever way you want to break the array into smaller arrays, like, you can use it. So you don't have to use slice. You can use I think you can use splice, but I know that splice mutates, I think. So I just don't use splice very frequently because of that fact. But yeah, it's not really the important thing isn't the slice. It was breaking the array into smaller arrays with each function call. Great questions. Are there any other questions you guys have?